very much, Daniel, for the kind introduction, and thanks a lot for having us here. Looks like a fantastic venue. We were in the building next door for the past week discussing cosmology, so it's nice to get even a larger crowd of people to discuss with. And I'm very excited. The week looked really like a fantastic program, so I look forward to chatting with many of you. And so the organizers tasked me to give an overview of what has been going on in the field of cosmological correlators. I have to confess, it was extremely painful to put together this overview. I had to look many things that I didn't understand, and I have to present them as if I understand them all, so I'll try to do my best. But in hindsight, it was also very useful for us to reflect on our own community as we are presenting it to other communities. So I thought it was very worthwhile exercises, and hopefully some of the ways in which I'm presenting it will give opportunities for other people to see interactions and cross-contamination of ideas with other fields. So without further ado, let me get started. I'm going to talk about cosmological correlators. And I would like to start really with the general motivations of why we even care about cosmological correlators. So I'm going to mention 4 facts about cosmology that I think everyone should know. They are surprising. I think they have important implications, and they really motivate why it's important to study these objects. And then I'll try to answer the obvious questions. What is a cosmological correlator, and how do I compute one? I think that if I satisfy that, then my task is done here. At least I've said what that is. And we will see that the answer is going to be, there's going to be more than one answer, more than 2, more than 3, and perhaps even more than 4 or 5. So let's see how we go. And then I wanted to give you some more recent results about these objects and how they are constrained by fundamental principles such as unitarity, causality, and in some cases locality. And then in the very last few minutes, I thought I would choose a sample of 1 or 2 topics of very recent research, and I tried to choose some that I think connect well to the study of amplitudes. Okay, so here are 4 things that I thought were very surprising when I studied them, and every time I go back to them, I do find them surprising, and I think they really underpin the interest on this field. So here they go. The first one is that you look up in the sky and you see the distribution of stuff across cosmological scale. Anything you can measure, as long as you can see it, or such as light and galaxies, then you know its distribution. Even if you cannot see it, like dark matter, you can still estimate its distribution. And the surprising fact that is to trying to understand how things are distributed, we are forced to go back to the first fraction of a second of the Big Bang and talk about extremely high energy physics, talk about dynamical gravity, which we have to quantize. So that's the first motivation for the field. The second one is that the thing that we're actually measuring is a single mode called the adiabatic mode, and that really nail it down what is the focus of the field. The third is that what are the properties that so far we have been able to explore of this perturbations. So far, henceforth, I will call these initial conditions the perturbations of the universe. And finally, I will try to make a clear connection between theory land, which I think where a lot of this conference will be living, with observation land, which is how we measure these things, to make it clear that the 2 are pretty tightly related. Okay, here to the left, what I'm showing is that you look up in the sky, you put on your microwave glasses, and you see this amazing picture that looks exactly the same color in all directions, because it's extremely isotropic. But then you really put your high definition and very precision microwave glasses, and you start seeing some tiny deviations in the color of the sky in different directions. And if those glasses are really good ones, they also see polarization. You can also map the polarization in the sky, and you put little lines at different points in the sky. So that gives you 2 maps. We believe that those maps really describe the distribution of photons on very large scales. And one surprising fact is when you correlate these 2 maps with each other, and you plot the result in Fourier space, or rather more precisely as a function of the spherical harmonics on the sphere, you find that there are very interesting patterns of correlation, anti-correlation that are shown here to the right. Most of that is not surprising. It's due to simple plasma oscillations. But what's surprising is that if you plot here what would be the horizon scale beyond over which causal effects can propagate, you find that it only covers part of the plot. Only the right-hand part here can be affected by causal physics. And everything to the left of this, within the hot Big Bang, cannot be affected by causal physics. And yet perturbation, you see here in this circle, they are anti-correlated. So this is an uncontroversial and very clear evidence that if we want to talk about distribution of stuff in the universe, you have to go to the first fraction of a second before the hot Big Bang. Okay, so there is no disputing this fact, and that's why we believe that this is really an interesting way to experimentally probe high energy physics. By the way, I should have mentioned, feel free to interrupt me if you have any questions, either technical one or more outsider questions on what the general motivations are. I'll be very happy to build them. Okay, so the second is that, okay, so now we decided we have to go back first fraction of a second before the hot Big Bang. What is it that we want to predict? In principle, you could try to predict the distribution of galaxies, which those are the easiest one to see, or the distribution of light in the universe. Most of it is in the microwave background, or the distribution of dark matter, which is harder to see, but there is a lot of it. It turns out that if we look at the initial condition of all of these quantities, they were all distributed the same. This is perhaps one of the craziest things that I've ever learned about our universe. If you look at small perturbation, let me call it the density of this quantity is rho, and small variations of that, delta rho. And delta rho of x, it means that different points in space have a different value. And you rescale them by the average density and the average pressure, you always get the same function for any one of these substances. And I'm going to call this function zeta of x. Just for concreteness, I will give you a nice interpretation of that. So this is not the first universe you would come up with. If you had to start the universe yourself, you would probably put different lines for different constituents. But that's very different from what we observe. So this is an interesting piece of the puzzle. And I would say it's not clear as of now what is the one explanation for this feature. But I thought I would mention it. So the name of the game is predicting correlator of this one variable. How can we interpret this variable zeta? Well, it's interesting because it can also be interpreted as the curvature of space-time itself. So in some sense, if you write the metric of an expanding space-time as an FLRW metric, so minus dt squared a squared dx squared, well, you could have a different amount of expansion at different point x. So here in this point x, the amount of expansion a of t could be slightly different from this, and that difference is measured by this scalar field zeta. That is the same variable as we saw in the previous slide. So in some sense, the distribution of curvature and the distribution of matter is also the same in our universe. And so most of the observations have been, and the theory has been eventually dedicated on the phenomenology side to understand this object. This is a good time to mention that if 30 years ago you had been told, try to predict the perturbations in our universe, you would have said, and in fact that's what Starobinsky said, well, I know one thing, that there should be gravity. Gravity is gravitons, so I better compute the distribution of graviton. That seems the most obvious thing. And in fact, gravitons do appear in how perturbations are distributed. However, so far we haven't seen them. As far as we can tell, if there are primordial gravitons coming from before the hot Big Bang, the amount of power they have has to be less than 3% of the scalar, and perhaps much less. People are spending, and have spent, billions of dollars to look for gravitons, and precision will improve enormously in the next few years, but so far we haven't seen them. But presumably, computing correlators also of spinning fields, such as the gravitons, is also going to be an interesting part of the story. Okay, so the scalar perturbations, we have measured them, because if you look in the sky, there are galaxies, and they're not exactly homogeneously distributed. There are small differences from place to place. And so they obey some statistical property. They have a probability distribution function, a PDF. And the PDF is very simple to write down. It's basically a Gaussian, so e to the minus zeta squared, where this zeta is the field, and the variance of the Gaussian is 10 to the minus 10 in terms of initial conditions. So this is summarizes quite reasonably what we know about this statistical field. And what we would be interested in is to go beyond this Gaussian approximation and to see if there are deviations from Gaussianity. And so far we have not seen them, so we have put bounds on any deviation from non-Gaussian distribution, in which this deviations compared to 1, which is the Gaussian theory, have to be smaller than approximately 10 to the minus 4, 10 to the minus 5. As far as observations go. However, on the other hand, we know that the theory of the universe should include gravity, and as was discovered a long time ago, maybe a century ago, gravity should be a nonlinear theory. So we know for sure that there are deviations from Gaussianity, and this is the main motivation why we know eventually you will have to see some signals that go beyond what we are seeing now, and that's what we are preparing for. In fact, we know that gravity, being a nonlinear theory, sets a lower bound on how much non-Gaussianity that can be, which is roughly speaking, and I'm sweeping under the rug several technical aspects, of the order of this parameter FNL being 10 to the minus 2. So humankind will measure this one day, perhaps soon, perhaps late. And so it's definitely an important target for both theory and observations. Okay, so so far I treated this field zeta as if it was just a number when I gave you the PDF, but it's not a number. It depends on x and y. And so here we really have correlations as a function of space. This is the third really surprising thing, is that if you ask the correlation between one point x and one point y, as you change the distance between these 2 points, actually in the initial conditions, that correlation does not depend on the distance. This is in some sense unlike anything we ever compute when we talk about particle physics or properties of quantum field theory in flat space-time, where we expect the correlation functions to decay, for example, for massless particle as 1 over the distance square, or exponentially for massive particles. But this is not what the initial conditions of our universe look like. It's actually easily seen if you take that map that you had before from the cosmic microwave background and you throw out the polarization and you correlate it with itself. It also has these nice peaks that come from plasma oscillations, but you can remove those because we understand plasma oscillations very well. And you rewind that perturbations to their initial condition, and you find that they're approximately scale invariant. So the amount of power as a function of wave number is almost the same. There is only a 3% deviation from exact scale invariance. The reason why this is important is that it suggests that if we want to study the generation of this perturbation, we should have a mechanism that explains the scale invariance, and the best mechanism so far that has been proposed is to study quantum field theory in a space-time that has that scale invariance as an isometry, and that space-time is de Sitter space-time. So a lot of the effort on this field has been trying to learn about and understand quantum field theory in de Sitter space. So de Sitter space is the same as an FLRW space-time, the space-times of cosmology, but scale factor is exponential in time. And just like Minkowski is a maximally symmetric space-time, so it really gives you hope that you should understand quantum field theory just as well as you do in Minkowski in de Sitter, but I would say we're at least half a century behind of what's understood in flat space, if not more. Many new conceptual questions arise that we don't know how to address at the moment. Finally, the fourth and last thing that I wanted to mention in terms of motivations is that all of these things are really closely related to observations. So suppose you go up, look up in the sky and make a map of temperature using your microwave glasses, or of galaxies, or of neutrinos, if you were really good at it. In fact, it doesn't matter what it is. You just make this map and measure endpoint correlation functions of it. This is what all cosmological surveys give us as data. This is the left-hand side, and you can do endpoint function if you're very powerful. Well, the promise of cosmology is that it's linearly related to the quantum correlation function of this field in de Sitter. This linear relation is crucial here, and it's valid only on large scales, but on large scales it is valid. And this delta here are so-called transfer functions. Some people spend their life computing them. There is a huge effort on the cosmological community to compute them. For the standard model of cosmology, they're very well known to sub-percent precision. So for the rest of this talk, they can be considered some given. And since you have this is what you measure. This is a direct measurement of endpoint quantum correlators. Let me also stress that if you believe that the very early universe was really described by something that is not a field theory, maybe some quantum gravity, perhaps some string theory, something else, then that's what you should use to compute this quantity. This is really the quantity that is being measured here. Okay, so this is the motivation behind the field. If you remember one formula going home, the take-home message is that this is what we measure. We know the transfer function. Anything we can say about these quantum correlators really will make important predictions for observations. So the rest of the talk is going to be reviewing how our community has been approaching the problem of learning and saying as much as possible about the correlators of these fields. Maybe this is a good time to see if there is any questions or clarifications or comments. Yes, please.
Categorize as unequivocal proof of the existence of a graviton.
Of a graviton as a classical, as a quantum particle. I think that would be, it's a long discussion of how we measure, so that maybe just to set the stage, the assumptions is that we believe that the origin of perturbation is quantum, because the quantum descriptions gives us the correct two-point function and gives us a natural way to set up initial conditions that we wouldn't know how to set up. The initial conditions just come from vacuum fluctuations, in some sense from the uncertainty principle, and that works. However, as of now, we don't have a smoking gun to tell that these perturbations are quantum in origins. So I would say it would be very compelling evidence that also the graviton is quantized, but it wouldn't be direct observations of the quantum nature of the graviton as a particle, even if we observe primordial gravitational waves. Yes?
What difficulties arise when you do QFT in de Sitter space?
Oh, yes. So there are many of them, and maybe as I go through it, I'll try to emphasize maybe 5 or 6 of them. But I think it's better if I show them as they come up. Let me mention maybe just a few of them. We don't know what is the correct ground state. There is no unique ground state selected by the symmetries. We have different type of divergences that happen due to infrared effects. We don't know exactly what are the rules of a consistent UV completable quantum field theory. We have much fewer results, and many of them tend to be perturbative and at very low order. So we don't have a century of calculations as a theoretical data set to play with. But there will be a few more that I mention as I get. Yeah, maybe some last question. Yes. Okay, then I'll set the stage. This is what we want to compute. I will just talk about these cosmological correlators. Can I tell you a little bit more about what they are? So as I made it clear, we have reason to believe that primordial universe was described by this metric, minus dt squared, a squared, bx squared, where a is exponential of time, the Sitter space-time. Most of the time, I will use this metric written in these coordinates, are also called conformal coordinates or Poincaré patch. In this coordinate, you see the metric is just proportional to Minkowski. So a lot of the connections to Minkowski physics will make more evidence by writing it in this way. However, the metric is not flat, it's only conformally flat. There is a function of time in front, which is a, which in this coordinate is 1 over eta squared. And that's one of the complications that come in. So one of the effects of having that function of time in front of the metric, since you were asking, is that in the Sitter space-time, energy is not conserved. It's not a good quantum number. And so all the time integrals that you almost get for free when you do, for example, compute amplitudes, now they will require extremely hard work. And that is one of the technical challenges of the field. So energy is not a good quantum number. And because of a lot of our intuitions of how physics is organized, is given in terms of energy, that has been an obstacle in translating our flat space intuitions into curved space-time. In other words, you can take a wave of some energy, and then because of the expansion of the universe, it gets stretched. So that is not a good quantum number to use. Okay, here it's a conformal diagram of the Sitter space, which is the square, and what we're using for cosmology is this top left triangle called the Poincaré patch. This diagonal line is the infinite past. Sometimes you would call it the Big Bang. That's where we would set some initial conditions. And this horizontal line here is so-called the future boundary, but it's really a conformal boundary. This space is infinitely big in the future. And that's where we want to make our predictions. I put this one here to contrast it to maybe what you would do in Minkowski, where you're trying to predict either amplitudes of massless particles or of massive particles at future infinity or future null infinity. And so the name of the game is to say as much as we can about the state of the universe on this surface, given that you assume some initial condition. For all of this talk, I will assume this so-called Bunch-Davies initial conditions. That is the unique state of the system that has all the de Sitter isometries, and it corresponds to the same vacuum as in Minkowski if you look at very short distances. For example, if you have a very small lab in a big expanding universe. This is a very well-motivated state, but it should be said that one of the key differences is that we don't control this state. It's not that we were there and we could ensure that the initial state was this Bunch-Davies state. That is perhaps in contrast to particle physics, as I will discuss in a second. Okay, so cosmological correlators, well, it's just the correlators you know from quantum mechanics. You take some Hilbert space that describe your infinitely, your very large system, which is the universe. You call that state omega, and then you compute the expectation value of some product of some local operators at different points. Since we have translation invariance, we like to work in Fourier space, but we don't have translation in time. So we don't like to work in frequency space, but we usually keep time as time. And then you take the product of these and compute the expectation value. So that is what a quantum correlator is, very generally. What we actually get to measure, since we were not there doing experiment, is only these correlators when all of this time are the same and they're all zero. So only the endpoint correlation function at equal time in the future. That's what we actually measure. But of course, theoretically, to understand quantum field theory, we should try to compute all possible correlators at all possible times of all possible type of fields. What we get to measure is only the correlators of massless fields, because massive fields decay. But theoretically, we should probably understand fields of any mass and spin. So coming to your question, there are a few interesting things that are different from amplitudes in flat space, for example. One is that the natural object of interest here is a correlator of fields. So this is a naturally and intrinsically field-dependent quantity. Okay? I have to tell you what field you should compute the correlator of before you give me the answer. We are not measuring particles. There is no detector ticking corresponding to particles. And so these objects are not field redefinition invariant, and I think it's a good thing because that's not what we measure. However, it does make it harder to compare with some of the manipulations that we do when we try to talk about on-shell quantities in flat space. And it does make it harder to think of what the correct variables are when we're working with gauge theories. The second is what I mentioned, is that we don't have experimentalists that spend 10 years trying to be sure that at the center of our detector is really empty and no one left a can of beer or something like that. Here, the initial state is just selected by our universal history. And so we can assume that this state was this Bunch-Davies. We have strong theoretical reasons to assume that, but it's not something that we get to control. Perhaps it's not so difficult, not so different from particle physics if you think of hadronic colliders, in which there is also some uncertainty as to what you're actually colliding, but that's perhaps nevertheless a difference. And finally, we really have to talk about time, and when you talk about time in GR, you have to choose coordinates. That's another complications that you don't have when you do flat space. Okay, so that's the object, and I hope it's clear that there is, in some sense, there is one and only one object that we want to compute eventually, or that we have interest in. However, there are many different, yes, please.
Thank you.
Yes.
Are those sort of disfavored because of some reason, some observations?
They are disfavored because if you lived in the de Sitter universe, which was controlled by an alpha vacuum, and you went on very short scale, you had a very small lab and you were doing experiment, the vacuum to you would not look like the vacuum we have in Minkowski. It would have an infinite amount of energy compared to that. And so that's the selecting property. So if the universe has to transition in a smooth way from an early universe to today at short scales, it seems that the Minkowski vacuum works very well to predict scattering amplitudes, for example. So we believe that the vacuum of the universe should be compatible with that, and that justifies not looking at alpha vacuum. In order to make alpha vacuum have a finite amount of energies compared to Bunch-Davis vacuum, you have to truncate some of the excitations, but that breaks the de Sitter isometries. So then they are not really motivated as de Sitter symmetric states anyways. Excellent. Okay, yeah, so the point is that there is one object, but there is more than one way of computing it. Oh, sorry. Yes. In fact, I'll tell you 4 or 5 different ways of computing it. And as I prepared this talk, I felt a little embarrassed in telling you that there are 5 different ways of doing it. But it really made me reflect on how our community, because of these many different ways, has been developing a lot of results and knowledge, but that is spreading more horizontally than vertically because different people find different results in different languages. And this is perhaps a sociological difference from thinking flat space, where, of course, you also have a wide variety of techniques, but eventually they're easier to compare to each other in terms of a scattering amplitude, for example. While here, things are going to take quite a different form if you look at them superficially. So let me mention what they are. The first one is perhaps the most traditional and the most studied one. It's going to be called the in-in or Schwinger-Keldysh formalism. The second one is going to be the in-out formalism. This is perhaps the third one is the wave function formalism. So now we're going to the Schrödinger picture rather than Heisenberg picture. The fourth one are going to be Euclidean methods, and they're going to look a bit different because there is not a unique Euclidean rotation that is useful, unlike in Minkowski. There will be a rotation that brings us to the sphere and a different rotation that brings us to ADS, in particular Euclidean ADS. And all of this have been used in the literature, sometimes even 2 or 3 techniques in a single paper. That makes it harder to really track results across the literature. And finally, there is perhaps more recent techniques, cosmological bootstrap, polytopes, differential equations. I'll only briefly mention this because Austin will give a talk on differential equations after me. Okay, maybe just to convey the message that although all of these are all different ways of computing correlators, they all are different ways of evaluating a path integral on different contours. So the left-hand side of this plot represents this line represents times from minus infinity here to the left to the origin, which is the future. This is this conformal time eta. However, you can make that complex, and then you can look at the complex eta plane. And then the in-in formalism is the one in which you integrate over this contour. You go and come back. This is different from the contour that we use, for example, for the LSZ reduction formula to compute an amplitude, in which we go from the infinite past to the infinite future. So even here, there is a second formalism that is much more similar to what we use for amplitudes. It's going to be the in-out formalism. Then another formalism is that you compute half of these contours, and that represents a bra and a cat. That's going to be related to the wave function formalism. And finally, one big rotation of this contour to the vertical axis is what connects us to all the results that have been obtained in ADS, specifically in Euclidean ADS. And the sphere is not visible here, or at least not in an obvious way. It's not the Android. Okay, so now I'm going to show you some of this different formalism. I'm going to give you just a 1 slide or 2 slides review. So the in-in formalism, sometimes even people call them in-in correlators, but I really refrain from doing that. The correlator exists irrespectively of how you compute it. The correlator is the correlator. The in-in is a way of computing it. So the in-in says, okay, let's go to the interaction picture. That's very useful when we do perturbation theory. There is some initial state. You evolve it with some interaction unitary evolution operator from minus infinity to a time eta, and then you insert. This evolution operator is the familiar time-ordered exponential of minus I, the integral of the Hamiltonian. You expand that to any desired order, and you get Feynman rules from it, and you compute. So pictorially, you start with a vector, you evolve it forward, it becomes another vector with the same length because it's unitary, insert an operator, and you do the same for the bra and for the cat, and that's the result. If you do this, you will find that there are 4 propagators. That's already a bit annoying. They are sometimes called G plus, G minus. They just depend on whether you're expanding the time evolution operator to the left or to the right. One of those 4 is just the familiar time order point function. Another is the known time order, just two-point function like Whiteman function. And the other 2 are the complex conjugates of those. So that already makes it the bookkeeping more annoying. Moreover, these propagators, they are actually really Hankel functions in Fourier space and hypergeometric functions in position space. And so you should remember that they will appear inside time integrals corresponding to the vertices because we have to do the time integrals. So even at 3 level, we will have to do for a vertex with V interactions, V nested time integrals of products of Hankel functions, which is pretty nasty at 3 level. Moreover, that actually was not even the worst news. If you have just a single, people in amplitudes, of course, complain that there are too many Feynman diagrams, proliferation of Feynman diagrams. Even here, even for a single Feynman diagrams, you have 2 to the V different terms to compute because every vertex in that Feynman diagram can come from the left and from the right, and they give different results. And it's only when you sum all of these 2 to the V terms that you get a real result as appropriate for correlators of Hermitian operators. Okay, so you really have to keep them all in. That's annoying. This corresponds to this contour here. It's called the in contour. Okay, so of course, what about the in-out correlators? We love them in flat space. That's what we LSZ project to get amplitude. They can be defined here in a similar way. Now you prepare the graph from the future and the cat from the past, so there is just one time evolution operator from minus infinity to plus infinity, and you insert correlators. This gives us an in-out formulation of this with the appropriate I epsilon prescription. So this looks like you go from the past, evolve, insert something, and keep evolving to the future. This is by far the least studied case. I think that we proposed this just about a year ago. However, I thought I would emphasize it here because it looks the most similar to what we do in flat space. There is only, everything is inside the time order, and so there is only one propagator, which is the Feynman propagator, time order 2-point function. But it has been the least developed of formulations so far. And you can just see graphically that this is going to be equivalent. You take the in that I showed you before. You had the line that goes from minus infinity to plus infinity that sends the vacuum onto itself. And this part cancels, and so the in becomes the in-out. So that's graphical non-perturbative proof that this is equivalent. And now you have to divide by vacuum bubbles to get the right result. The advantage of this in-out formalism is that, as familiar from Minkowski, you get one Feynman diagram, and there is one contribution, one product of Feynman propagators. You don't have to sum over 2 to the V of them. And so that makes it simple. And many of the results that we know in perturbation theory, they're probably more naturally expressed in this in-out formalism. The drawback is that you have to integrate over a second copy of the Sitter space, but I will not discuss that in detail. So that was formalism number 2. Formalism number 3 stems from the observations that we don't have Lorentz invariance to begin with. We're really computing correlators at some time. There is a preferred foliation of the universe. Presumably, the interactions we care about are not Lorentz invariant, or at least not boost invariant. And so there is really not a good reason to ditch the Schrödinger picture. That's actually a good picture. That's why we learned quantum mechanics in the Schrödinger picture the first time. Then we forget about it when we do quantum field theory. So how does the Schrödinger picture work in quantum field theory? You start with a state of the system, some vector in an infinite dimensional Hilbert space, and then you project it on a basis. A convenient basis are field eigenstates, because you want to compute expectation value of fields. So fields eigenstates are a very good basis. And this gives you a functional that is called the wave function, sometimes a field theory wave function. This functional is a big beast, like a scattering matrix is a big matrix. This is also a big functional, so we cut it up into pieces. We parameterize this at the exponential of some unknown coefficient psi n that I will call the wave function coefficient times arbitrary powers of all the fields that we have, all the fields in the standard model, all the fields we don't know about, all the gravitons and perturbations of the metric. They all should appear here in phi. And then if we know all of this coefficient, then we compute the state of the universe. And from that, we can compute anything we like, in principle, just by following the well-known Born rule, in which you take the expectation value weighted by the wave function of the operator, and then you normalize. This is a different formalism. And this has attracted a lot of attention in the past 5 years, so a lot of the effort has been going in this direction. So here, you're just time evolving once, and then you project, but you don't come back, because you know that coming back is just a complex conjugate of going forward. This was the third formalism. How do you compute this wave function? Well, it is described by a path integral that goes forward only once, weighted again by some functional that you call the action. There's only one propagator in this business, it's time order, but it has an additional boundary term reflecting the fact that we are solving a boundary value problem in which the wave function is constrained to take a certain value at the end. There are fewer diagrams, but then you have to do 2 steps. If you want to compute a correlator, you first compute the wave function and then use the Born rule. So it's a 2-step procedure. Every step is simpler, but then when you do both of them, you're back to the same amount of algebraic complexity. And really the way I think about the wave function is that the wave function is to correlator the same that amplitudes are to cross-sections. We do measure correlators like we do measure cross-sections, but we find it more convenient to talk about amplitudes and wave function because they display the structure of the theory, such as unitarity, in a more explicit way than the observables do. And of course, once you have these more primitive objects, then you can go to the observable by taking the mod square, as familiar in quantum mechanics. Euclidean methods. So if it was Minkowski, then it seems the natural way, the only abstraction to be Euclidean is that you have sent to T to I tau. But here there are various ways of doing it. And one analytic continuation is the following. Consider, so here maybe I went backward. Let me start with the de Sitter metric. This should be L squared. This is the inverse Hubble. And it's minus the eta squared plus the x squared over eta squared. This is the metric. If you want to get rid of this minus to make it Euclidean, well, you should send eta to plus or minus iz, where z is going to be some Euclidean coordinate. That is going to give you a minus here, and then you can get rid of 2 minuses by also analytically continuing the radius of space-time. And then you land on the Euclidean ADS metric, which is just hyperbolic space. A lot is known about this because of the study on ADS CFT. And so a much studied technique is to do this rotation, use the ADS result, and come back. If you do this and you use the boundary correlators in Euclidean ADS, those that are computed by a conformal field theory, then you get the wave function coefficients in the Sitter. That's the connection. While if you want to have the correlators, then you have to do some linear combinations of different diagrams to represent the plus and minus branches of the init contour. And one technical difficulty is that you have to do opposite rotations for the 2 branches, so you get more cumbersome in explicit calculations. However, the big advantage here is that you can use all the powers of 20 years of ADS CFT literature, which gives you many results. And finally, the penultimate method is to use the sphere. That's a different rotations in which you write the Sitter in global coordinates, and you rotate the time coordinates from tau to I theta, and that this just becomes the familiar metric of a sphere, and you can use all the results that you have from spherical harmonic decomposition. This has also been used a lot. It's a bit harder to make the connections to what we are computing so far, because on the sphere there is no clear future boundary where you're supposed to do your calculations. So that emerges upon analytic continuation. But this is another very interesting method. And finally, one last method is this idea of the cosmological bootstrap that I wanted to mention. So far, all of the methods I've discussed, you see some correlators, you try to make up a model that gives you some action. In that model, you do calculations, so you specify the action, you get some Feynman rules, and then you calculate all the correlators, endpoint functions. Of course, the models you write down, they're not completely random models. They should obey some general properties. They better be unitary if you want the predictions to be interpreted as probability. They better be local. They better respect the symmetries. So the idea of the bootstrap is to see if this step can be bypassed by using these symmetries and principles to go directly to the result, or at least write down the structure that the result must have. Good, okay, so that kind of brings me to a summary of all of this. So given a model, the way I've shown you, for example, GR plus some scalars, you actually can sit down and compute. We understand what the Feynman rules are. Instead, we have 5 or 6 sets of Feynman rules. The calculation is hard. You have V-nested time integrals of products of Hankel function already at 3 level. And so even something as simple as a 3-level massive exchange that I think a 6th-year elementary school kid could compute, because you tell them vertex times propagator times vertex, and they know multiplication, so they could compute it. Here it was only computed 6 years ago. Because here you really have to do 2 nested time integrals of product of Hankel function. That's hard. Spinning correlators are even harder, or maybe just as hard. The 4-point function of graviton, something that you would think, okay, well, maybe it was computed 100 years ago when GR was written down, was only computed a couple of years ago in CITES. And I'll show to you the result. There are many different methods, as I hope I've emphasized. And I realized that emphasizing that, you might think, oh, God, this seems like a big mess. I never want to have anything to do with cosmological correlators. However, the point, the silver lining of this is that if you are trying to see if there is some interesting technique that you're familiar with that can be used for correlators, and you find one particular integral that describes correlators that you don't like, just choose a different one, or yet another one. Eventually, you might find a way to formulate the problem that looks very familiar. So I just wanted to encourage people to look for different entry points, because there are really many different formalism, and they take very different forms at the explicit level. We have little theoretical guidance of what theories we should be using. Except for having GR, we don't really have the whole rest of the standard model of particle physics. Loops are extremely unexplored. I would say that we don't fully understand how to compute them, and even less renormalization is understood, let alone any picture of the renormalization group. So there is still much to do. Okay, so I wanted to tell you about a few properties, but maybe I should pause to see if there are any comments and questions.
Can I ask, trying to understand, so you said that the nested time integrals involve these Hankel functions, but Hankel functions have been studied for centuries now. At least for small cosmological constants, I would have thought that some interesting asymptotic expansions are known. Are they not useful in calculating these integrals?
Yes, so there are definitely useful expressions, and people do use them, and you find names such as upper functions, and you encounter hypergeometric functions with very large integer next to them. As far as having a small cosmological constant, in some sense, there is not such a thing as far as we are concerned, because we are really interested in computing the correlators on very large scales. And so no matter how small the cosmological constant is, we take every energy scale to be even smaller. So once you really select this late time value, you have really lost a connection to flat space, except some interesting analytic continuation. So there is really not a perturbation in how small the cosmological constant is. That's not a good expansion. Excellent. So I wanted to give you quickly an overview of some properties of these objects. Something is known about their causality, locality, and unitarity. And for all of this discussion, I will assume that we have isometries in terms of translations and rotations, as well as dilations. which is why we came into this business of the sitter, because we like dilation, because they give us scale invariance. But they will not assume invariance under boost, the equivalent of Lorentzian boost, because it's likely that every interesting model will break that as a symmetry. Good, okay, so what do we know about analyticity? So we know that there should be some deep connections between analyticity and causality. It is often hard to establish this connection, even for amplitudes that have been studied for a very long time. There is still debate as to exactly what are the generic consequences of causality for endpoint scattering amplitudes. So what can be said about cosmological correlators? And here I would say much of what is known at the level of the wave function. So the starting point is that you try to, again, find an off-shell definition of what the wave function is by saying that the energies are arbitrary, unconstrained variables. So in some sense, you amputate the external legs of a correlator and substitute them with off-shell legs with frequency omega, and later on you can choose this omega to go on shell if you want to find the object of interest, and k here are the mode functions for an arbitrary frequency. And then what is known is that on the complex omega plane, where you keep all other frequencies fixed, you can prove non-perturbatively that in the lower half complex plane, you expect no singularities. So there is some interesting non-perturbative consequence of causality. And all the singularities in perturbation theory, at least, appears to be on the negative real axis for the wave function coefficient. However, there are some surprises. So there are common features from Minkowski in which three-level diagrams give you poles on this axis. However, the order of those poles in the sitter is not just order 1. They can have arbitrarily high order poles. And loop diagrams give you branch cuts. However, there are different cuts that appear compared to flat space. So there are amplitude light cuts that you recognize. Oh yeah, I know this cut has come from the threshold where I produce 2 particles. But there are new different cuts in which you only cut part of the diagrams that don't have a corresponding equivalent in amplitude. So you can call them wave function cuts. And they have been classified within perturbation theory. So that's part of the knowledge. And explicitly, the analysis was performed for Minkowski, but at least for massless and conformally coupled field in the sitter, the analytic structure should be similar. Yes, Johanna. Oh, sorry, yes. Here I was assuming, here I was going back to assume boost invariance. Sorry, I apologize. Yes, I should have said. Yes, yeah, that was confusing. I went back to assume boost invariance because even there I think there are some open questions even before. But you're right, that gives me the opportunity to mention that there's been some study of, even in flat space, what happens when you break boost. And there you open, well, a Pandora's box of phenomena that are relatively unexplored. And eventually we will have to understand that if we want to understand it in the sitter. Yes, excellent. Locality, I would say, is the least understood of this concept. You might think from flat space, well, usually you phrase locality in terms of cluster decomposition, the fact that correlation function factorize at very large distances, but because of the expansion of the universe to arbitrarily far away points, where one's very close to each other, so there is not really this traditional notion of cluster decomposition. In fact, I showed you very early on that the 2-point function, and that's the reason we like the sitter is because the 2-point function doesn't depend on the distance. So it really doesn't cluster factorize. A weaker property is manifest locality, in which interactions are just the product of fields and their derivatives, a finite number thereof, at the same time. And this does give you interesting constraint on wave function coefficients, such that their derivative with respect to the norm of external momenta has to vanish in 0. So this is a very interesting property. It's called the manifestly local test, and has revealed to be very useful in explicit calculations. It's valid for light scalars and spin 2 massless fields, such as the graviton. But really much more should be understood about locality from a more fundamental level. And for example, even just the commutator of fields outside of the light cone, the consequences of that for general correlators, I think, have not been completely understood. Then there is unitarity that really plays the lion part as far as constraints from fundamental principle goes. Of course, we want probabilistic predictions to make sense, so we need a Hilbert space with positive definite inner product and unitary operators implementing time evolution. And a lot of that is known and has been leveraged heavily in the past many years for computing and constraining amplitude. Like the engine of much of that is the optical theorem or cutting rules. So what's the story in cosmology? Well, this wasn't very clear for a long time because in cosmology we really don't observe an evolution from one state to another. We just observe the final state. So it has been hard to phrase constraints on just this final state rather than comparison between the initial and the final. But there are constraints. So perhaps a very useful one is the cosmological optical theorem. So at 3 level, this stems from the simple observations that if you have a unitary theory and you take this particular combination of the wave function coefficient plus its complex conjugate, where you analytically continue both frequencies and momenta, this vanishes at 3 level. Okay, so it turns out that you can trace this property to all orders in perturbation theory with any number of loops. Just by working a little bit harder. So if you define this very specific combination, you call it a discontinuity, just using a similar terminology, although notice that the definition of discontinuity is slightly different from what we have usually in mathematics. Then you can define general diagram by diagram rules that tell you the discontinuity of any diagram to any orders in perturbation theory. And the rule is the following: take a diagram, take the discontinuity. That means color the internal line and sum over all possible ways to cut those internal lines. Here there is only one, so only one way to cut it. Cutting means that you substitute that line for 2 lines that go to the boundary. Now you separated this diagram into 2 3-level diagrams, and you take the discontinuity of each one of them. Of course, when you separate them, they become lower order diagrams, and this gives you the general expectation that unitarity in perturbation theory relates higher order things to lower order things, and that's why it's useful. This is actually valid to all orders in perturbation theory for any number of loops. So here I gave an example, and I gave this example to emphasize that there are really many different cuts that you have to sum over. It's not just a single cut that separates the diagram. For example, this cut and this cut and this cut, they're all different, and you have to use them all to find the result. And these have been also useful to study loops, because of course loops are cut into 3-level quantities, and this leads to reasonable simplification. So I think that, and maybe the last one that I wanted to mention, because it's really cool, is non-perturbative. There are some non-perturbative results at the level of the 2-point function. This is a curved space-time generalization of the Cullen lemma decomposition. It says that any 2-point function can be written as integrals of the free 2-point function times the spectral density that is positive by unitarity non-perturbatively. And it's somewhat similar in flavor decomposition of the 4-point function in terms of conformal partial waves. Also features a positive definite spectral density. And so this is what has been worked out in the literature, but probably much more should be done and should be leveraged to get interesting results. Good, so I wanted to use the last 5 minutes to mention 3 active research directions that have been looked at in the past few years, especially with the goal of emphasizing maybe a relation to amplitude, as well as what we believe are open problems or things that we really don't understand. So this is a very biased sample of the literature. So the first one is that effective field theories, we use them, we talk about them, but I'm not sure that we have really a foundational understanding of them. We are really missing something like a Wilsonian picture as we have in flat space. And I think that should be one of the next steps of the community. So many of the aspects are very different in the sitter space. For example, even how we organize different scales, since energy is not conserved, it seems that's not the right variable to organize the discussion. Here I wanted to focus on just one specific difficulty, which is when do effective field theories break down? That usually is part of the package when you're given an effective field theories, and we use many in particle physics, for example, in QCD and flavor physics, which is a nice connection to the topic of this workshop. You want to know when it breaks down. That's really important. So there are a couple of ways of doing it. One is that you compute the next order. And that's good. However, it's a bit disappointing because if you compute the next order, why didn't you keep it to begin with? So more often you estimate the next order and you get bounds that are not really sharp. You just estimate the next order and perhaps in terms of scaling, you can see the validity, but not sharply. Often unitarity gives you sharp bounds, and the most famous one that comes from amplitudes is the bounds on the amplitude of partial wave coefficient. For example, if you expand to two scattering in Legendre polynomials, the coefficients are bound to be to have a real part which is less than a half. We have not been able to use this extensively because of the question that you asked before, is that there is some sense in which the object we are looking at, we have already taken a late time limit that makes it impossible to connect to the flat space limit because of an order of limit issue. And so how do we diagnose really the breakdown of effective field theory in cosmology has been a matter of debate. One proposal here is to try to find a more unifying notion across space-times, which perhaps comes from entanglement. And so the idea is to think of effective field theory as really fundamentally as being a separation between the degrees of freedom that we keep and the one that we don't, and to use some kind of entanglement of those degrees of freedom as a notion of when this effective field theory is valid and when it is not. So imagine you have an effective field theory that describes a certain range of scales, even though this is hard to make precise between some infrared and UV, and then you separate your Hilbert space into an environment part and a system part. And let me say that the system is just going to be a single Fourier mode, because we can compute this correlation function, we can also compute them for a single Fourier mode. And then you can trace over the environment, and you're left with a density matrix for a single mode density matrix. And that density matrix has to obey unitarity bounds. It has to go between 0 and 1 if probabilities are to come out right. So there is a purity of it, which is the trace of rho squared that has to have this property. It's bound between 0 and 1. And you can compute that object in perturbation theory and see if it obeys it. The beauty of this, the advantage of this is that you can define this in Minkowski and curve space-time just the same, in fact, in any space-time. And so this really gives you a way to compare the range of validities of effective field theories across different space-time, which you otherwise would not be able to. In perturbation theory, of course, everything looks like a constant plus coupling constant square plus higher order. And so this cannot possibly be bounded because it's an inverted parabola. So eventually, if you plot this purity as a function of coupling constant, eventually it becomes negative. And so that violates unitarity bounds. So this tells you that definitely your perturbative description has to break down at some point. And this is kind of the intuition of why it does. We have done the exercises of using this to compare bounds that we get from partial wave unitarities in Minkowski to bounds from purity. And interestingly, they all scale in the same way. So it seems that they're capturing similar ways in which effective field theories fail to work when wider and wider separated scales are introduced. However, the numbers are always different, and purity bounds tend to be slightly weaker. Perhaps an interesting aspect of this, which really underscores a main difference between amplitudes and correlators, is that purity bounds are field redefinition dependent. So if you can take a theory like this interaction here, d phi square, phi times d phi square, which is a field redefinition of a free theory. There are no bounds from partial waves because all amplitudes are 0, but there are purity bounds. And that is very useful because we want to compute correlators off field. And so we need some diagnostic that knows about the fields we are using to organize our Hilbert space. I think my time is almost up. Just one slide. 4-point gravitons. There has been a lot of interest in the amplitudes of spinning particles. Famously, for gravitons, amplitude in Minkowski takes this beautiful, simple structure when written in terms of spin-orellicity variables. Do we see any of that simplicity or structure emerging in cosmological space-times? This has been computed. The graviton 3-point function was computed 15 years ago, or maybe 20. but the graviton 4-point function had not. It was recently computed using cosmological bootstrap techniques as well as brute force calculation. And this is the result. And these are the name of the functions that appear in the result, such as WS, WS, and WC. This is getting ever so smaller because the point I want to communicate here is even though we have the result, it doesn't look simple by any stretch of the imagination. And so one of the obstacles here is that we believe we are not using the right variable in this. And perhaps Facundo will have something more to say about this in his talk later today. So let me come to the last slide. There has been also recent effort in trying to define the scattering amplitude in the Sitter space. There are many conceptual problems that unfortunately I don't have the time to discuss, but at the moment there are maybe 4 related proposals in the literature for this, and this is promising because it really allows you to import many techniques. In particular, as far as we can tell, at least 2, if not all of these definitions of a de Sitter scattering matrix obey some optical theorem, therefore some non-perturbative notion of unitarity. And the open problem that I wanted to emphasize here is that we are really trying to derive the Sitter native positivity bound. What separates effective field theories that do and do not admit a consistent UV completion in the Sitter? So far, no one has been trying to do the analysis in a de Sitter native environment, but people were only importing the results from flat space. So, sorry for rushing, so I'll just leave the slides here with my conclusions, saying that motivated by cosmology, people have been studying correlators. We have learned a huge deal, but it seems that there are many very basic and presumably very general facts about quantum field theory in curved space-time that we still do not understand, and so this is a wide open field. Thank you very much for listening.
Okay, thank you very much, Enrico. Yeah, it's a huge topic, so 1 minute over. 1 minute over is not. So, yeah, question.
You motivated studying these de Sitter correlators by this approximate scaling symmetry, this primordial. But then you never seem to say much about scaling variance in de Sitter. Where are you using it in constraining these things? Everything was in momentum space, so you had translations, rotations, but what about scaling variance?
Yes, it was. I left it very implicit because of time, but it was always implicit in the choice of variables. So just like for amplitudes, the first thing that you do is to select some Mandelstam that are Lorentz invariant. Here, when you write an object, the first thing you do is to say it only depends on fewer variables because overall rescaling can be taken out by scaling variance. So it reduces the number of variables that the function that you're trying to compute can have by 1. And that is done. So the result that I written down, the optical theorem, locality, they actually don't require that. But if you have 1 fewer variable, then it's much easier to guess the final function because you have a simpler functional dependence. So technically, it is used in that way.
Another question there, maybe?
Yeah, can you comment a bit more about observations and how much of these calculations can be constrained by them?
Yes. So far, the only thing that we have seen is the 2-point function of the zeta variables, and there are maybe 5 or 6 other things that we are trying to look at. So this would be maybe a whole talk on observational updates, but let me mention them. One that I mentioned was tensor modes. We haven't seen them, so that would relate to the correlator of spinning field. Another one would be higher n-point function, and the 3-point function is the first one, and perhaps the 4-point functions. That's called non-Gaussianity. A third one would be deviation from scaling variance. If even scaling variance could be battery broken, so that's another attempt. People look for that already in the power spectrum. Another then is that, is there some other primordial perturbations that are not zeta, that goes under the name of isocurvature perturbations? And the other one is whether other symmetries are broken, such as isotropies. I would say all of this will see a large improvement in the next 5 to 10 years, partly from large-scale structure surveys that will measure mode three-dimensional modes in our universe, and so can improve on some of these things by an order and a half of magnitude, depending on what you're talking about. And then, yeah, I think I want to leave it to that.
In fact, there will be a talk on Thursday on observations by Misha Ivanov. Okay, so maybe we cut it off here. You can ask Enrico more questions in the break, but let's thank him again for a nice talk.